Okay, so we have been looking at finite state machines in a certain degree of detail. One of the things which is related more in the context of how we would implement arbitrary or slightly more complicated circuits and not necessarily to do with finite state machines is this concept of how we can parameterize designs, right? And this is a very useful thing that we will be making use of quite a lot as we move forward. So, I am going to spend a little time talking about the notion of parameters and how we can use that in order to make our designs more flexible. So, parameters are so called compile time constants. So, what do we mean by a compile time constant? It means that it is something that does not change at runtime. Now, in the context of Verilog, which is used for implementing hardware, keep in mind that the runtime is not even the simulation. The runtime is actually after we have synthesized and created a set of gates and actually implemented it in hardware, what are the what kind of behavior does it perform? That is runtime for us. Now, what that means, for example, is that certain things such as am I dealing with a 4-bit number or an 8-bit number or a 12-bit number has to be decided at compile time, because that literally decides how many pieces of hardware, how many units of hardware I am going to deal with, right. It is not something that I can change at runtime. Now, even in a language like C, such a thing could potentially have been done at runtime. I could have some way of sort of reflecting on the code and deciding whether something should be treated as a 16-bit value or a 32-bit value at runtime. In hardware, that is simply not possible, because you have to decide how much hardware you need and build the circuit correspondingly. So, parameters in that sense are compile time constants. They are evaluated during the compilation process, which means that even Verilog simulation handles them as something that is done at one shot as the system is being elaborated or expanded out before doing the simulation. Now, they are typically declared using a couple of different keywords. One is parameter and the other is localparam. The difference being that parameters sort of apply throughout the entire file in which they are declared, whereas localparam can be inside a specific module and sort of is similar to the idea of the scope of values or variables in a language like C. So, you can have module level parameters and local parameters, right, and they have their each has their use cases. Parameters also have types associated with them. Typical parameter types are integers because they can be used to specify just numbers. They can also be real valued parameters, right, and this is a bit more tricky because it is not very clear what a real valued parameter means in the context of hardware, but there can be contexts in which it is actually used. You could also have a parameter that is a string, and this is almost certainly not synthesizable, right. So, the only context in which you would use a string parameter and most likely even a real valued parameter are in test benches. There are also ways by which you can override parameters that we will look at briefly in the coming slides. So, this is an example of how I might define parameters at the module level, right. The parameters that I am interested in, I basically have a module whose name is counter, and as you can see over here, this portion essentially defines the inputs and outputs of the system, right. So, this bit before that is something that did not exist all this while, right, and if you look at it, basically contains a parameter and another parameter definition out here. And what we have is the first parameter width, right. It is again a convention to use capital letters for parameters to make them easy to sort of identify even in the text, although it is not absolutely mandatory, you can use a mix of characters. The width parameter is set to 8. This is basically the default value. If I do not override it somewhere else, the width is that I am going to use over here is going to be 8. And I also have another parameter called max value, which I am defining to be 100 out here. So, let us see where it gets used. The width parameter, as you can see, is straight away used out here, right. Rather, I want my count to be an 8-bit value, and therefore, rather than defining this as 7:0, I define it as width minus 1:0. And since width was defined as 8 over here, I basically get an 8-bit output. The interesting thing is, as I mentioned, you can override parameters. Therefore, while instantiating this counter block somewhere, all I need to do is change, let us say, width to 16, and I will basically automatically get a 16-bit value for count. Right. So, this becomes very useful in terms of how we can actually change and have one definition of a Verilog module and then use it to instantiate different blocks with different parameter sizes. This is an example of what that instantiation looks like. I would basically give the type of block that I am trying to instantiate, which is the counter. I give it a name, right, my underscore counter. If this was in a test bench, it would probably be called DUT, but over here it is not inside a test bench. I am actually just instantiating this probably in some other Verilog block, okay. But the interesting thing is I have overridden the parameters that I had over here, right. One of them basically says change the width to be 16. The other one also says change the max value to be 200. Now, where is max value being used? I don't know. It is going to be used somewhere inside the definition of my module. But wherever the value max value gets used over here, since I have done an override of max value to be equal to 200, inside my code I will find that max value takes the value 200. This happens at compilation time. It is like a defined macro equivalent in C, right, where essentially as soon as it basically goes through the synthesis or the compilation process, for all the rest of the design, max value takes the value 200 and completely ignores the value of 100 that it was originally defined with. Now, one thing to keep in mind over here, my width has been defined as a 16-bit value, but when I instantiate this block, this signal count signal has to be declared in my parent block, the one that is inside which I am actually instantiating this. So, I have some kind of a top level block, and inside this I have my counter, right, and this count signal is essentially a wire that is present inside this top level block, which means that it actually needs to be defined as a 16-bit piece of logic, right. This definition has to occur at the top level. Only then I can use it properly over here and get the appropriate behavior that I expected. Otherwise, what could happen if I don't, if I override a parameter but then don't define it properly over here, I end up having a mismatch, which is almost certainly not what I would like. Now, you can also have registers that are configurable in width, or you can also have some kind of a shift register which is a configurable thing in depth, right, and this sort of brings about an interesting way of writing code that we will just go through in a little bit more detail. I have two parameters over here, width and depth. The width seems to be reasonably clear and easy to understand. It basically says that, you know, as long by default it is an 8-bit value, therefore logic width minus 1 data in, logic width minus 1 data out, okay, with minus 1 colon 0. But now look at this definition out here, right. This is a interesting definition. It basically says that logic width minus 1 colon 0, you can think of this as the data type, right, as the equivalent of an integer or something like that, and then it gives the variable name stages and then says depth minus 1 colon 0. Effectively this is like an array of elements, right. What it is saying over here is one element is a 8-bit value, and I want to have stages which is a set of, let us say, 4 registers, right. So, this is basically a set of 4 registers, sorry, let me just, right, each of which is an 8-bit value. Right. So, we have a combination of basically 4 8-bit values, right, and this is essentially the variable that I am calling stages. Now, the interesting thing is, as we can see on the right hand side over here, right, stages of I can be used to refer to the ith element within that. Now, let us look at this code in a little bit more detail. This is essentially how we are writing the code for this. What you can see is while reset, I write a for loop, and what I say is the for loop basically goes from 0 up to depth and it sets stages of I to be 0. Else, if the shift enable, that is to say we are out of reset and the shift enable signal is equal to 1, Stages of 0 gets a value from data in. Notice that this is a non-blocking assignment, so that update actually happens at the end of the always block. It is, in other words, a sequential circuit and actually gets implemented as a flip-flop. I then have this for loop that basically says stages of I equals stages of I minus 1. All these remaining 1 to depth minus 1, right, a total of depth minus 1 different executions of this for loop will get activated concurrently and essentially cause all these values to sort of shift, right. I have a register, I have another register, I have another register, and each of these values basically shifts. What goes in here? This is data in, right. This is 0, this is 1, 2 and 3. This is essentially the notion of a shift register. So what has happened over here? We have managed to define a parameterized version of a shift register. Two things are parameterizable. One is the width of the register, which is 8 elements, and the second is the depth of the register, which is how many different elements it has for shifting. Where does such a piece of code actually become useful? Well, this is more or less what a first in first out buffer looks like, right? Although there are more efficient ways of implementing these things, and therefore it's likely that this is not exactly how it gets implemented. But for example, if you were to try and use this in the context of, let's say, a filtering application, this is more or less exactly how the code would look. The question of how exactly does a for loop get converted into hardware is something that we will look at later. The short answer is it basically creates n copies of this particular line, right, one with each. It basically expands out in the for loop and writes it out completely and says that, okay, I will actually treat this as n, or in this case depth minus 1 different instructions, right, one after the other. Now the for loop that we saw over there was a very simple form of for loop. A more sort of useful, potentially useful approach in Verilog is this notion of something called a generate statement, right. And what generate statements can be used is that they actually generate multiple different instances of a block. An example is over here, right. I have a generate and generate block out here, inside which I have a for loop. Now this for loop looks like a regular for loop, except that this is called a genvar. It's not an integer, right. So what does that mean? It basically says that this is now going to be treated as a generate statement, which literally means that this for loop is going to get unrolled, right, or it will result in the creation of num inputs or 1 to num inputs, in this case num inputs minus 1 number of different assignment statements. It is as good as writing those out actually in parallel. So this is almost like a macro expansion, right, one way of thinking about it, but it's a bit more intelligent in the sense that it actually sort of gives you labels. Add stage will then be appended with add stage 1, add stage 2 and so on, which allows us to actually go into detail over here and identify how each and every one of these things is connected, right. So it's the equivalent of actually creating, it allows us to create arrays of different hardware units and connect them up in very systematic and simple ways. So it can be a very potentially powerful way of creating hardware, especially hardware that is sort of repetitive. Okay. And it is synthesizable, and what I mean by that is that since after all what it is doing over here is basically creating n copies of this, and once that is done the for loop goes away, the generate goes away, effectively it's as though I had actually physically written out n copies of this assign statement. And as long as that assign statement by itself is synthesizable, or maybe it could even be an instance of a block, right, it would actually create n copies of that block, and therefore that is also valid synthesizable Verilog. You can also have something called a conditional generate. Now this once again is a slightly artificial example, but I am just using it to explain how you might use something of this sort, right. We are potentially talking about something, let's say we want a variable type counter. A variable counter, what I mean by that is it could be of different types. The width of the counter is something that can be parameterized. Whether we should increment or decrement is something that can be parameterized. We could even have something which decides whether we are working with active high or active low reset, right. But the interesting thing is I am only going to show you one particular way by which the sort of compile time, the generate can be implemented, which basically says that I can put in a generate and generate and say within that, if the parameter wraparound is set to 1, instantiate this logic, wrap logic, which basically says next count is count plus increment, and if that exceeds the value of all ones, right, go back to 0, else do count plus increment. The other thing is saturation, which basically says that if count plus increment exceeds this value, then just set it to all ones, else set it to count plus increment, right. Now what this means is at compilation time, as long as your parameters are defined, it will have either this assign statement or this assign statement, and the other one actually completely goes away from the logic. It is no longer there after the point that you have instantiated and given a specific parameter for the value, specific value for the parameter wraparound. So why did we do all of this? The main reason why this comes up in the context of finite state machines is because finite state machines typically tend to have reasonably complicated, they are already one of the more complicated forms of digital circuit that we can come up with for implementing, right. And in that sense, the ability to have compile time control over the different configurations is very useful and important for us. Parameters should be used for such compile time configuration, right. You should always provide default parameter values in general, otherwise the compiler does not know what to do. Derived parameters can be implemented using local params, right. You can actually say local param, let us say the product, right, width into height or something of the sort. So width into depth might be total number of bits, for example, or I could have something else where I specify the depth of a FIFO and I could actually use a function like log in order to compute how many bits are required in order to address it, right. Those are derived parameters. Now when you are designing something of this sort, the important thing to keep in mind is you need to be responsible for verifying that your design works across all parameter ranges that are considered valid. You can also put in some conditions which basically say what, check whether the parameter falls within a valid range and possibly just error out and not even allow synthesis to proceed if you are outside that range. Consider the resource utilization impact. It is very easy to write a parameterized design which can completely blow up, and because keep in mind that it is actually creating n copies of whatever you write, right, and it is entirely possible that it, by giving inappropriate values for the parameters, your entire system sort of goes completely out of control in terms of the size that it actually requires for implementation. At the end of the day, there is no substitute for proper documentation. You need to document what are the valid parameter ranges and what are the constraints on the system. Use generate blocks for structural changes, right. As we saw over here, when I want to actually have multiple instances of a particular block or multiple structural instantiations, a generate block is perfect for something like that. And again, convention, right, follow consistent naming for the generated blocks, that makes debugging easier. And similar to the verify designs across the parameter ranges, try and have test cases for each parameter combination, especially the corner cases that you think could potentially lead to problems.